Hello everyone. Today we are going to see the Cotter joint, and this joint that again we can call it as a socket and spigot joint. So what is the use of this joint? This joint we normally use to connect the two axial rods which are subjected either axial tensile or sometimes compressive force. To connect the two shafts that we are using this Cotter joint. Now this is the Cotter joint. In the Cotter joint, three major components are there. One is the socket, then second one is the spigot, and third one is the cotter. This is the first socket, second that is spigot, and third this is the cotter. These three parts are there and we are going to design here. Now there are the few dimensions that already we have seen, that the three parts: socket, spigot and the cotter pin. So this is the front view, top view and side view of this Cotter joint. This is actual component, the Cotter joint which we use. So its view. Now few applications that we will see where we can use the Cotter joint. Here we have enlisted view. The joint between the piston rod and the crosshead. So here this is the crosshead and the piston rod that we are using. Here we are inserting that pin, and that is the cotter pin we can say. So this is the one of the application, that is the joint between the piston rod and the crosshead of the steam engine. Then second one, the joint between the slide spindle and the fork in the valve mechanism, that also we can use. The third one, we can see the joint between piston rod and tail of the pump rod, and even fourth one, in foundation bolt also we can use this joint. So these two figures are the same one. Here again that is in our bicycle that we are using the Cotter joint. So these are the few applications where we can use this Cotter joint. Before going to design, again we are doing some assumptions in this. What are those assumptions? First, we enlist it as the rods are subjected to the axial tensile force, right? So whatever the rod is there, so here this is the shaft, and that we are assuming that on this the tensile force it is acting. So this is the first assumption. The second, the effect of stress concentration due to the slot, it is neglected. Now see, here when we are joining this, here we are making one slot, and we know that whenever there is a sudden change in cross section, there the stress concentration effect it occurs. So due to this slot, whatever the stress concentration is there, that we are neglecting for our the simplification. And the third one assumption that we are making, the stress due to the initial tightening of the cotter are neglected. Now if you see again here, that we are pressing this cotter pin in the downward direction, and here that the dimension, if they fit closely or even we press some, apply some force, then it becomes very tight fit. At that time this pin, it will exert some force on the socket or the spring, and due to that whatever the stresses are induced, that also we are neglecting. So these are the few assumptions that we are assuming here in case of the Cotter joint. Now, so this is about the force balancing in case of this Cotter joint, this is in the socket, this is the pin, this is the spigot. Okay, for going to the design, we will see this video, then we will come to know how the failure of the component it takes place. So this is a rod on which there is a tensile load, and due to that here it will fail. So this is the cross-sectional area which it is resisting to the tensile failure. Again, in case of the cotter pin, so it will fail due to the shear. So this is the shear failure, and the resisting area it is shown here in the red color. Then again, due to the tensile load, the socket end it will fail. So this is the red color area, it shows where it failure occurs, or the area which it is resisting to the failure. Again, the same socket, but it fails due to the shear. So here shearing it is occurring. So this is the area which it resists to the shear failure. Similarly, shear failure of the spigot. This is the area which resists the shear failure of the spigot. Now the tensile failure of the spigot. So here the failure it occurs. Now this is the red color area which it is resisting to the failure. So this area we have to consider while designing. Now I hope you understand when we say the tensile failure of the socket, tensile failure of the spigot, shear failure of the socket, shear failure of the spigot, then shear failure of the cotter pin, how it fails, that you might have seen in this video, and I hope you have understood that what is the resisting area. Okay, now we will see one by one how to design this. So first we are going to design that the spigot, and again we are assuming that we are applying the tensile force on that, right? So due to that, whatever the failure it occurs, this is what the area which it is shown in the hatch. So this is an isometric view. If you see the side view, so here it is there. So that is the area resisting to the tensile failure. Even if you see here, it is enlarged, that the diameter it is d2, and whatever the slot it is there, that is for the pin, cotter pin which you are inserting, that is not resisting, so that we have to remove. So this hatching area we have to calculate, so which is the resisting area to the tensile failure. Now we will calculate. So the resisting area is what? Pi by 4 d2 square. So this diameter it is d2. Pi by 4 d2 square when I will take, then the whole solid area you will get. But here inside there is one slot that we have to subtract. So therefore minus what we will get. So this thickness into the depth. So we will get d2 into t. If you subtract, then this hatching area you will get. So this is the area which it is resisting to the tensile failure. Therefore, we know the tensile stress in the spigot that will be given sigma T is equal to, that is the load upon the area. So load is what? The tensile force P which we are applying, and the resisting area just now we have calculated, that we will put. So in this way we can find out the dimensions, that is the T2 here, because the load they have given and the material which we are using, they have given the maximum stress or the load carrying capacity of the material. So from that the unknown is D2, that we can calculate Z. So this is how the tensile failure of the spigot that we can calculate. Now the next, the shear failure. So just now we had seen that due to the tensile it will fail here, but due to the shear it will fail here. Now see here clearly. So this is the area which it is resisting to the shear failure. Now when the shear failure occurs, there is the double shear. So you see here, here is the one area which it is resisting to the shear, and again here in the top side. So there is the double shear. Now this is the area first I have to calculate, and as there is a double, so I will multiply it by 2. Now, so double shear, what is the area? Shear area is equal to, now see here, this is the area A into D2. So A into D2, when I say, it is area of the only one side. Now again on the another side, so the total shear area, if I have to calculate, A is equal to twice A into D2. So this is twice, means that is what, for the double shear. Here and here the double shear it is occurring. Now shear stress induced in this spigot, the tau is equal to load upon area, we know. So therefore tau is equal to load given P and the total area which it is resisting to the shear failure, just now we have calculated, twice A into D2, that we will put here. Then you will get the what is the shear stress induced this. So given, if you rearrange this, then you will get P is equal to twice A D2 into tau. Now the third possibility, you can check either it may fail by the crushing of the spigot. Now see here, due to the application of this force P, there is compressive force on this area. So whatever the area is there, on this there is the compressive force, right? Similarly here I will draw, and there is a compressive force. So this is the area which I am showing, it is under compression. So this is the thickness T and the diameter it is D2. So this is the resisting area for the compression. So therefore the crushing area is what? This is the T and D2. Just now I had shown this is the hatching area. Here that is the compressive force it is applying. Even you can see here the same area it is there on this side. So this is thickness T and this is D2. So therefore the crushing area is what? T into D2. Then crushing stress, we are denoting it by sigma C is equal to again load upon area which is resisting to the failure, that is under the crushing. So this T into D2. So therefore sigma C is equal to load upon area T into D2. So in this way you can find out the crushing stress induced in this. So we have designed this spigot, first by considering the tensile stress, second by considering the shear stress, and now we had seen the third considering the crushing stress. So we considered all these three types of stress. In the similar way, we are going to design the socket end. So the first in the socket, tensile failure. Now this is the socket where the dimensions are T2 is the inner diameter of this socket or the diameter of the spigot, just now we calculated which or in the earlier stage, and this outside diameter of the socket is the T1. Now when there is a tensile force acting on this, so here is the least area, right? So here it will fail, and whatever the hashed area is there, that is resisting to the failure. Now see here, this is the solid, it will not fail, and there is possibility from this end to, if you consider here, from this end to here, it may fail. And again, as we are providing the slot here, so here is the less resistance in this region, so somewhere here it may fail, right? So that is what the area here they have shown. So hash area which it resists to the failure. Even this, the color it shows the failure area. Now here the enlarged dimension, that this is thickness T at pin which we are inserting in this, and the inner diameter, that is D2, outer diameter it is T1. Now this, the red color which it is there, that is the area which it is resisting to the failure. Now we will calculate what is the tensile stress it is induced in this. Now first we have to calculate this area. What is the area? Now see, the area is equal to, so this is the first, we will consider it as a hollow circular shaft. Now when I take pi by 4 d1 square, then the whole area you will get. Out of that I have to subtract this minus pi by 4 d2 square. Then pi by 4 I will take common, so therefore I will get pi by 4 d1 square minus d2 square, means the hollow circular shaft you will get. But again, as we are providing here the slot, so that area we have to subtract. So therefore I will take this minus. Then what we will get, this d1 minus this d2 means this thickness. So this and this you will get, right? So this, and then this thickness I have to multiply, then this area and this area you can subtract. So d1 minus d2 means this length and into this thickness t, so that I will subtract. So this is the area which it is resisting to the tensile failure of the socket. Once we calculate the area, then we can find out the corresponding tensile stress. Sigma T is equal to load upon area. Now whatever the area we have calculated just now, that we will put here, then we will get the corresponding tensile stress induced in this, right? And if you rearrange, then you will get this equation, right? So sigma and area they have multiplied and they put P as it is. So this is the area and this is the sigma. So therefore you can calculate the corresponding the tensile stress induced in this. Now next we can see the shear failure of the socket. Now first we had seen that the tensile failure, so it may fail like here that we had seen. Now it may fail due to the shear also. So how it fails? Shear, here it is, right? And the area which it is resisting to the shear failure, that is shown here, the hatching area. And again see here, the shear failure is at again two sides. So here it is one shear area and again here it is the another shear area. So here the double shear area is there. Now what are the dimensions? Because anyhow we have to calculate the area which is resisting to the shear failure. Now here the outside diameter it is D4 enlarged diameter of this socket, then inside diameter it is D2. So then D4 minus D2 means this area, this length you will get, and if you multiply it by C, then you will get the hatching area. So the same view. Now the area which it is resisting the shear failure, just now we have seen D4 minus D2, this length and this length, and then this thickness, that is the C. So this is the area which it is resisting to the shear failure. And again the two area, here this is the one on the another side, the two. So therefore the total area, if I have to calculate, then I will multiply it by 2, double area I will get. Then once you get the area, you can calculate the corresponding shear stress induced in this. Now therefore the tau shear stress is equal to load upon the area. So therefore the area which we had seen, that we will put. So tau is equal to P upon twice in bracket d4 minus d2 into C. So in this way you can calculate the shear stress, or the reverse, if you have given shear stress and the load, you can calculate the corresponding dimensions. So d2 already we have calculated. In case of the Spigot, the unknown will be d4. That d4 you can calculate in the both way. Now the third, the crushing failure of the socket. Now see, the shear failure it took here, and again the tensile failure it took here. But if it is not failing due to the tensile and due to the shear, there may be possibility of it may fail due to the crushing, means the compressive. So here this is the T and the depth, it is the D4. So here the enlarged dimension they have shown. So this is the area which it is resisting to the crushing failure, means the compressive force it is acting on this, and this is the area which it is resisting to that compressive failure. Now this area how to calculate? Again similarly, d4 minus d2, then you will get this length, and if you multiply by thickness t, then you will get the area which it is resisting to the crushing failure. So same diagram. The force P causes the compressive stress on a narrow rectangular area of this thickness T. So that area is equal to d4 minus this d2, then you will get this length and this length, and if you multiply it by t, then you will get the area. So therefore the crushing stress sigma C is equal to load upon the area. Area just now which we calculated, which is resisting to the crushing failure. Now see, again in case of the socket also, we considered either it may fail the tensile, either it may fail the shear, or it may fail due to the crushing, and we have to check all these possibility. Now we will see the last, that is the cotter pin. Now the cotter pin it may fail due to the shear when the component is new and there is no any tolerance in between, it is the tight fit. So then the only shear failure it occurs. So it may fail here and the here, right? So this is the spigot and socket, and this is the spigot, and whenever there is a joint of these two, at that place the shearing it may take place. So the two area where the shearing of this pin it may take place. So here and the here. Now so this is what the width P and the thickness T. If you see thickness, that is the T, and width it is T. Now if you want to calculate the area, right, the same figure here it is, this is thickness and this is the width. Now again the double shear, here it is the one shear and here it is again the double shear. So this cotter pin again it is failing due to the double shear. So now we have to calculate the area which it is resisting to the failure, shear failure. What it is? This T into B. So this is the top area we will get, and again as it is taking the double shear, then we will multiply it by 2, means that we are considering the top area and the bottom, or this area and here. So therefore the area P into 2, this is the 1, and as there is a double shear, so therefore twice P into T. So therefore we know the stress tau, shear stress, is equal to the load upon area. So in this way you can find out what is the shear stress induced in this, or the maximum shear stress carrying capacity of the pin they have given. Then based on that you can calculate its average width or thickness, right? So in this way you can find out both things. Now when we use the pin, and due to decay and corrosion erosion, the part it may wear out and the contact becomes loose. At that time there is possibility of the failure of this pin due to the bending. Then we have to consider that bending stress induced in that, or we can say either it may fail due to the bending. So here the few assumptions that we have to do, that the force P between the Cotter and the Spigot end is assumed uniformly distributed. Now see here, it is in this area of the pin is in the Spigot end, and from this end to this end we are assuming that the force is uniformly distributed. And the second, the force between the socket and the Cotter pin is assumed varying linearly, or you can say here this part of the pin it is in the socket, and again this part it is in the socket. Now on this pin the force we are assuming it is varying uniformly, so it is 0 and it is varying continuously increasing. So this is the uniformly varying, and again similarly on the other side also. So this is one of the assumption. Now this is the total force P it is there, and here the two parts are there. So this force it is divided P by 2 here and again P by 2. Now so we already studied in strength of material that if we assume this is simply supported beam, these two, and the point load it is, and the maximum bending moment we have to find out, then we will get the maximum bending moment at the center. So here we are trying to find out what is the maximum bending moment, means I have to take the bending moment here at the center. So that we will take. Now see, this is the pin. So here is the center. So this Cotter pin, that is the D4 distance, it is there. So this is the portion which is inside the Spigot, and this is the portion which is inside the socket. So inside the Spigot dimension it is D2, and on which the force P it is uniformly distributed, and the portion which is in the socket end, that uniformly varying load is there. So this distance we are assuming it as a Y. Now so when I consider the axis, this uniformly distributed load, it will act, we are assuming that it acts at the center. So this is the center from this end to this. So here it will act this load, as this is total P, half portion means that is P by 2, it is acting here. That distance we are assuming it as a Z, and as this is uniformly varying load, and when we are calculating, then that we convert into the point load. And when it is so we are assuming that from the 0 to higher end, so this distance is what, 2/3 of this total distance, and from the higher end 1/3. Once again I will repeat, from the lower end it is 2/3 of this total distance, and from the higher end it is 1/3 of this distance. This particular load it will act. So here this distance we are assuming it as a x. So this is P by 2. Now we will find out what is this x distance. This distance, so it is as just now we had said, from this total distance, this is 1/3 of this distance. That is 1/3 of this y. So this total distance is y, and from this higher end we are taking 1/3. So 1/3 of the y, this x will get, and x. This what is the y now? So this is the D4 minus D2. Then you will get this y and this y. And if you divide by 2, then you will get the only this distance, that is the y. So D4 minus D2 will get these two distance, and divide by 2, then you will get the y. The same thing here, we put the value of this y. Now if you rearrange this, then this 3 and 2 multiply, then you will get the 6. So you will get distance x. Now so this half portion, right, showing here we are taking the bending moment. So the two forces are there. One, this is P by 2, which is acting from this end to this. So this distance I have to know, and again this is p by 2, this from this distance from this axis. So when I take the bending moment about this axis, so what we will get? So this the point load. So this force into the perpendicular distance, and as it is rotating in the clockwise, so I will take p by 2 into this x plus d2 by 2, right? So p by 2 d2 by 2 plus x, and we know the x value, right? Already we calculated that, we will put later. But this first force into this perpendicular distance just now we kept. Then another one force is there, p by 2, and this it is rotating in anti-clockwise about this axis. So p by 2 into z. So this is again it is z, right? So what is that? Minus p by 2 into z. Now we will put the value of this x and the z in this. So what we will get? P by 2 d2 by 2 as it is. This x value we know, d4 minus d2 divided by 6, that we will put this minus p by 2. Z is what? This total d2, and this half portion is d2 by 2, and again it is acting at the center, therefore we will get d2 by 4, this z distance. Now we will rearrange this p by 2 I will take common, then d2 by 4, then I will get d4 minus d2 divided by 6, right? So d2 by 4, d2 by 2 minus d2 by 4, then 2 by 2 I will multiply, then 2 d2 by 2 minus d2 by 4, then I will get d2 by 4, and this term as it is. So this is what the bending moment you will get. Now I know the moment of inertia I. So if I take its side view, so this is what the thickness T you will get, and this is the average width B, and this is the area, right? So this moment of inertia, it is related to the area. So as this is the rectangular section, what is the moment of inertia? This T B cube by 12. So this is the T B cube by 12. Then again I need this distance y. What is the y? It is distance from the neutral axis. So as this is the rectangular, at the center you will get the neutral axis, right? So it is distance from neutral axis to the outermost layer. So this is distance y. So as this is total b, so from this neutral axis to outermost you will get the b by 2. Now we know the equation, sigma b is equal to bending moment divided by I into y, and whatever the value we just now found out, mb, bending moment, I and the y, that we will put in this equation. And if we put and rearrange, then I will get the b is equal to, by rearranging and cancelling the term, we will get the b, that is the average width of this quarter pin, is equal to under root 3p divided by t into sigma b in bracket d2 by 4 plus d4 minus d2 divided by 6. So in this way we can find out what is the width by considering the bending failure of the quarter pin. Okay, so I hope you have understood the design of the Cotter joint. Okay, thank you.